Hello everyone, this is Dr. Cothell. Welcome back to part 2 of thermochemistry. And in this section we're going to talk about a coffee cup calorimeter and how to calculate the energy involved in that. And then we're going to look at Hess's Law and see how we can calculate the energy or the delta H of the reaction using those. So there's two ways that we're doing this, okay? One is if we're doing it experimentally, and so we are going to do it actually in what we call a coffee cup calorimeter. And so we call it that because it literally is two coffee cups that are nested together, styrofoam, right? You have something to stir with, okay, and then you have a thermometer going in there, and it goes down into the liquid. And so you're going to actually do an aqueous reaction. It's at constant pressure because it's at room pressure and temperature. The calorimeter is interesting in that when you have constant pressure, the Q of the reaction is going to be the same as the delta H of the reaction. And how we calculate that is that we're going to take the negative of the product of the mass of the solution times something called C sub S of the solution times delta T. And C sub S stands for specific heat, and every material has its own C sub S, and so it's very specific. So it's never anything that you have to memorize unless it's water. Usually you use water a lot, but it's something that's going to be in a table for you that's already been figured out. And so when the delta H of the reaction is going to be equal to the Q of the reaction, all right, the Q of this, but the Q of the reaction is equal to the negative Q of the solution. Now, I'm going to show you what I mean by that in a minute. But ultimately, what we're going to report it as the delta H per mole of whatever our reactant is. All right, so as usual for me, I'm hands-on, so the easiest way for me to show you how to do this is to just run through one of them with you. And so if you look at this, we know what there are three distinct steps, okay? 1, 2, and 3. The first step is you get the Q of the solution, okay? The Q of the solution. Then the negative of that is the Q of the reaction, the heat of the reaction, okay? So, and that's why people get a little confused on, did the temperature go up or the temperature go down? If the temperature goes up, it's exothermic, okay? So it tells you the temperature of this solution rises. All right, so here is my reaction up here, and I'm given some information. I'm given 0.158 grams of magnesium metal and enough hydrochloric acid to make 100 milliliters. All right, and it is in this coffee cup calorimeter, and it doesn't matter what the concentration of the acid is as long as it's strong enough to cause the reaction to occur. So we're not quantitatively worried about the HCl, okay? When we do this, the temperature rises from 25.6 to 32.8. So since it rises, we're going to get a positive temperature change, okay? We call that delta T. So this is going to be the rise from 25.6 to 32.8. And so that is going to be a change of 7.2, and this is in degrees C, and we're going to leave it in degrees C. I'm going to show you why in a minute. And it's positive because it rose. All right, so it was a positive, it was an increase in temperature, and it wants us to find the delta H of the reaction, and delta H of the reaction is going to be in joules, in this case, per mole of magnesium. And it also tells us that the density of water is 1.00 grams per milliliter, just in case we need that. All right, so the Q of the solution, okay, it should say solution there, is equal to the mass, which in this case was 0.158 grams of magnesium, times C sub S, oh, and it told us the C sub S is 4.18 joules per gram times degrees C, okay? So 4.18, sometimes it's 4.184 joules over gram times degrees C, all right, and that's your constant. That's your specific heat of water. So the hydrochloric acid solution is dilute enough that it also has the same. And then times delta T, which we said was a positive 7.2 degrees C. All right, so in my dimensional analysis brain, what I'm going to do is I'm going to go back and I'm going to say, okay, I got rid of grams and I got rid of degrees C, and I'm going to be left with joules. And so when I do the math there, I'm going to get 4.76 joules. And that's Q of the solution. Q of the reaction is the negative of the Q of the solution. So Q of the reaction, this is a nice easy step, is equal to a negative 4.76 joules. And then to get the delta H of the reaction, I use the Q of the reaction, which is a negative 4.76 joules, divided by the number of moles of magnesium. Now I'm going to have to calculate that, right? So I had 0.158 grams of magnesium. And so in 1 mole of magnesium, if I look on the periodic table right quick, it's 24.3 grams. So when I do that, quick calculation, I'm going to get 0.0065 moles. So I'm going to divide that by 0.0065 moles. And that's going to give me a negative 732 joules per mole of magnesium. So that's how you calculate the coffee cup calorimeter. Your lab, if you're in my class, is going to involve a coffee cup calorimeter, so you're going to be looking at this particular calculation a little bit more when you do the lab. So of course I gave you one to practice with, right? Just remember the trick about getting number of moles. You've got, this is 0.100 moles per liter, and this is 0.050 liters. And if you multiply those together, you're going to get the number of moles, okay? Because you need to know that's important information for this particular thing, okay? All right, good luck with that one. These practice ones always make you think a little bit out of the box, okay? All right, the second part of this we're going to do is Hess's Law. Love Hess's Law. I like things that follow rules, just me. And so the enthalpy of a reaction is always associated with a particular reaction. What I'm saying is that the enthalpy is an extensive physical property. Okay, so it's extensive, so that means we know it depends on how much you have. So if you multiply the reaction by a factor, then the delta H of the reaction is also multiplied by that factor. Another characteristic of extensive materials is that if you reverse something, like if you reverse a reaction that it's involved in, then you reverse the sign of the delta H. So there's two main rules in this Hess's Law that you have to remember, and that is that it's extensive. So if you have to multiply this by 2, you're going to have to multiply your delta H by 2, because usually you're trying to figure out by balancing them what your overall delta H is going to be, right? And if you have to flip that reaction, you're going to have to change the sign. So it was negative up here and it turned to positive because I flipped this and went backwards from CO2 to C and O2. Now, if a reaction can be expressed in a series of steps, and most of them are, you know, you probably learned by now that it's not just one step in a reaction. Usually you've got at least a couple of steps, often more than that. All right, and so the delta H for the entire reaction is the overall sum of your individual reactions. So the delta H is for each one of those reactions. So like they're showing you that you put some energy in to go A plus 2B to get to C, and then C is going to give off energy and go to D. So in that, you're pulling some or absorbing some energy in, which would be positive delta H, and you're giving off others. And then the difference is this, okay, which looks like you have more of the negative delta H than you do the positive delta H. So Hess's law says that the change in enthalpy for a stepwise process is the sum of the enthalpy changes of the steps. All right, so how do we use that? Okay, these are really cool and they can be fun if you will just let yourself become one with them, okay? All right, there's nothing hard about them, okay? We're giving you the delta H's over here. And that's of each step in the reaction of this. Now we normally just write the overall reaction for you, okay? But in order for us to know what's going on energy-wise, we have to know what those individual steps are. And so what we have to do is, when we get done with this, we have to have this 3C plus 4H2 gives us C3H8. Now, I'm going to have to do things to those three steps in order to end up with this overall reaction, which I just rewrote here. And I rewrote it there so that I could see what I did to each individual reaction. All right, so what am I talking about? All right, so what I'm going to do is I just start on the left. You can do whatever you want to, but to me, I just go in order. So I'm going to look at that C. I have 3 C's in this final equation that came from up here. This is the overall reaction. So I have to do something to a reaction that has a C in it in order to have 3 C's when I get done. And so I have to multiply that by 3. As you know, that means I'm also have to multiply the O2 by 3 and the CO2 by 3, because I multiplied, if I multiply one thing, I have to multiply everything. That also means that I'm going to have to multiply my delta H by 3, okay? So that takes care of my 3 carbons. Next, I'm going to look and see what else is on the reactant side. Okay, well, that C3H8 is not on the reactant side, but H2 is. So I need to have 4 H2s. So what do I have to do to this reaction that has the H's in it? I got to multiply it by 2, because if I multiply it by 2, that's going to give me 4 H2s, which is what I want when I get done. 4 oxygens and, no wait, 2 oxygens, my bad, and 4 waters. That means I also have to do what? I have to multiply that by 4. No, by 2. By 2, sorry. I had to make it 4, so I had to multiply it by 2. All right, so the last thing on there, that C3H8 is showing up on the reactant side, but it needs to be on the other side, but I only have to have one of them. So I don't have to multiply it by a number, but I do have to do what? Reverse it. And what that means is, in the case of the delta H, then I've got to change the sign. Okay, I've got to change the sign because I reversed it. So let me show you what I did. I'm going to redraw it down here. All right, so I took the carbon, which was written the correct way, and I had to multiply it by 3 because I got to have 3 carbons when I get done. So 3, 3, 3. And then my delta H, remember these are kilojoules too. All right, that's going to be times 3. Then my H2, I need to have 4 of those when I get done. Okay, so that means that I have to multiply my H2 oops. So I got to multiply that by 2, right? Because I had 2 of these to start with and 2 of those. So when I multiply 2 times 2, that's 4. 2 times 1 is 2. And 2 times 2 is 4. And I'm going to show you why it's important to keep up with that in a minute. All right? And then the last thing what I had to do is I had to reverse it. Why? Because as it's written, it's writing my propane as a reactant, but my propane in this reaction is a product. So I'm going to reverse that whole thing, but I only need one of them, so I don't have to multiply it by anything. So this becomes 3 CO2s plus 4 H2Os gives me C3H8 plus 5 O2s. And then my delta H was now a positive 2,043 kilojoules. All right, so that's gonna, I don't have to worry about that one. So, and let me show you how you know you've done it right. So what I wanted to end up with is this, okay? So I have 3 carbons. I have 4 H2s. And I have 1 C3H8. Everything else in there should cancel. All right, so I'm going to look. All right, so I've got 3 plus 2 is 5 oxygens. And I've got 5 oxygens over there. So those cancel. I've got 3 CO2s on this side and 4 waters on that side and that side. So everything else canceled. So now all I have to do is the math. So this becomes a negative 1180.5 kilojoules. The one that I'm multiplying by 2 becomes a negative 967.2 kilojoules. And then I've got that positive 2,043. So the overall delta H of the reaction is going to be a negative 104.7 kilojoules. So, and I rewrote it because a lot of times people like to rewrite them because when they reverse it, they want to make sure they see what they're doing. Or if you think you're good, you can just do it on your own, okay? and just flip it in your mind and just do it. Because what you're looking for is the numbers. I always go and I check to make sure everything canceled, just to make sure I didn't make a mistake. And because sometimes you might have to multiply it by a half. All right, and so you got to make sure that you're following through with that on every single thing on each of those steps. And so I gave you a couple to practice on for this, okay? Sorry about the arrows. This one's kind of covered up, but you should have it on your in-class notes, and that's oxygen, right? Okay, and that's it. So we learned how to do the coffee cup calorimeter, and we learned how to do Hess's Law to find delta H of a reaction.